So, just a second. Okay. Yeah. Okay. Hi, everyone. Welcome to HEP Journal Club, ISO Mohali. So before we begin, I request the audience to please keep their mics on mute and unmute to add any comments or ask any questions. Today we have Dr. Jacky Kumar as our speaker, and I would like to take the opportunity to introduce him. So Dr. Jacky received his PhD in 2017 from TIFR Mumbai. After that, he was a postdoctoral fellow at University of Montreal. Currently, he is a Humboldt Research Fellow at Institute of Advanced Studies at Technical University of Munich. So today he will be talking about lepton-flavour non-universality. What can we learn from SMEFT? And so with this, over to Dr. Jacky.
Okay, thank you very much, Harpreet, for the introduction. So maybe we can start.
Yes,
okay.
Please.
You see my slides moving? Yep. Okay.
Yes.
So first, let me thank you, Vishal, Amresh, for organizing this seminar. It's pleasure to be present at ISO Mohali, at least virtually. So today I will be talking about lepton-flavour non-universality and what can we learn about it from standard model effective field theory. So this is the plan of my talk. So first I will introduce you what I mean by lepton-flavour universality in standard model. So this is a property which is present in standard model, and then I will talk about how can you test such a property of standard model. So as you know, we can test various features of standard model or any other theory through observables, which we test, which we measure at the experiment, and then see if they agree with the model or not. So this is a way to test the symmetries or any other features of any theory. So then, so as you might have heard that it started around 2014 when LSAB first time saw some discrepancy with respect to standard model. So basically LSAB measured some observables and they were not consistent with standard model. And after that, there has been many updates. One of them was in 2019 and then 2021. So consistently we see the coherent pattern of the anomalies starting from 2014 to till now. So I will talk about how can you how to interpret this anomaly using the approach effective field theory approach, and then I will spend quite a bit of time to introduce to you to standard model effective field theory, and then finally I will come to the main point of the talk, that what we can learn about LFU violations if such deviations are confirmed in the future experiments. Okay, so let us start with the lepton-flavour universality feature of the standard model. So yeah, let us start with from very basic thing. So as you know, in nature we have symmetries. Okay, so symmetry is some transformation which you apply on your Lagrangian, and if the Lagrangian is invariant under this, then we say that this is the symmetry of the Lagrangian. Okay, and as you know from Noether theorem, the symmetries give rise to conservation laws. So for a given symmetry, you have some implied conservation laws. Basically, that means some quantum numbers are conserved during some if you apply this symmetry. So this you can test again using some observables. So if observables predicted by your Lagrangian. So if so let's say S is symmetry of your Lagrangian, then that corresponding to that, you can look at the observables predicted by this Lagrangian, and this you can finally test at the using the experimental methods. So some of the symmetries, as you know, are exact. That means we haven't seen them to be broken in the nature. They are always preserved, and some of them might be broken. Okay. In fact, many of the symmetries, important symmetries which you see in standard model are broken at some point. So for example, standard model in particular respects the Lorentz invariance. Lorentz invariance. So Lorentz invariance, you can think of this as a rotation in space or plus a boost in space time. So if you exclude the space inversion and time inversion, I mean this is also part of Lorentz group. If you exclude this part of the Lorentz group, then this symmetry is exact. We have never seen at experiment any violation of this symmetry. So we can safely say that this symmetry is exact. Then we have a gauge symmetry. So as you know, standard model is built on the basis of gauge symmetries. In particular, this is the group of the standard model, SU3 color times SU2 left. So this means only left-handed fields transforms under SU2, and the right-handed ones are singlets, and then U1 hypercharge. So this is a full gauge group of the standard model, which is, as you know, is broken at the electroweak scale. Then you have this another gauge symmetry which is present at the low energy. So SU3 color and U1 electromagnetic. So this is never broken. We haven't seen any process, any observations at the experiment which indicate the breaking of this symmetry. So this we can say this is exact. So similarly, we have something called accidental symmetries. Okay. So for example, a baryon number or lepton number. So these are the symmetries which are present in your low energy effective Lagrangian, but these are not a priori, these are not axioms of the theory. They are just accidentally present in your Lagrangian. Okay. Baryon number and lepton number, for example, you can say they are kind of exact, because we haven't observed proton decay, which will indicate the violation of baryon number. And as you know, the proton lifetime is very, very big. So we can say that these accidental symmetries are exact. In the same way, we have something called charge lepton-flavour universality. So what happens is that the gauge interactions in standard model are universal. That means for all three families of leptons, like electron, muon, and tau, they have exactly same interactions with the gauge bosons. So this we call as a charge lepton-flavour universality. So the question is this symmetry, can this symmetry be broken or not? So the way to test is we look at some observables in which these interactions appear, and then see and measure them, and then see if electrons and muons and tau modes, if they are found to be equal, then it's not broken, like as we have in standard model. If we see some deviation, if we see, for example, that electron mode is behaving differently as compared to muon mode or tau mode, then you can say that universality which is present in standard model is actually broken. So there is no problem, right? As you see, some of the symmetries might be broken. So it's okay to expect that some of this symmetry might be broken. I mean, it's nothing. There is nothing sacred about any symmetry. So it is just a matter of testing. If you test at the experiment, if you found it is preserved, it's preserved, or if you found it's broken, then it's broken. Like we have many examples. So let us look at it. Look at the lepton-flavour universality property in standard model in bit more detail. So this is the part of the gauge sector of the standard model. So you know that we have this. Okay, so we have this doublets, lepton doublets, which has three families: nu E, nu mu mu nu tau tau. So we have three families of leptons, and then we have this. So these left-handed fields transforms as doublets under SU2, and right-handed fields transforms as the singlets. So this is the part of the Lagrangian, gauge sector of the Lagrangian. As you see, so here I have suppressed the Fermi index, but for all three families, like nu e, nu mu, or nu tau, the form of this Lagrangian is completely identical for all three families. Okay, there is no difference here. So here d mu is the coherent derivative, which as you know has a form something like d mu is del mu minus iota some coupling, and we have some symmetry generators, for example SU2, and then we have the gauge fields here. So when you expand this this term, for example, of the Lagrangian, you will get interactions of these gauge fields with the leptons or quarks as well. So we see that this sector is completely identical for all families of leptons and quarks. So now, if we look at corresponding vertices, so as I said, when you expand this Lagrangian, for example, this part, you will get interaction of Z boson with the leptons. So Li here, I is the family index. It can be E, mu, and tau. So for all three families, you see this vertex, the strength of this vertex is same. It has same Lorenz structure as well. Even the coupling strength is also same. Okay. Similarly, you will also get when you expand this coherent derivative, interactions of photon with the leptons, and this is also exactly same for all three families. So this is what we mean by universality, that all three families of leptons have exactly same couplings to the gauge bosons. There's only one thing which breaks this universality feature in standard model, which are the Yukawa interactions. But those are in that case, the strength of that interaction is proportional to mass. So as you know, leptons have small mass. So very safely we can say that LFU, lepton-flavour universality, is preserved in standard model. Okay. So now the question is how to test this feature. As I said, we can always look at some observables in which in particular these vertices enter. So we will look at some processes in which these vertices enter and then measure these processes, okay, for E, mu, and tau for each mode. So in particular, one possibility is you can have a B meson going to S meson through a loop. This is a penguin, famous penguin diagram, which is mediated by W boson and all type of quarks, U, C, and T. So this vertex basically is a charge current vertex and is proportional to CKM elements. Then you combining it with the spectator quark U in the initial and final state. So you can construct a B meson, B plus and K plus. So this kind of processes give rise to, for example, B plus to K plus, and then in the lower part you can connect a photon or Z boson, and this gives rise to the complete process becomes L plus L minus. So as you see, our important vertex is this vertex. Here you see the interactions of Z with the L plus L minus and photon with the L plus L minus appear, which as I explained in the previous slide have exactly same strength. So now if you measure, for example, B plus to K plus mu minus versus B plus to K plus E minus, in the standard model you expect them to be exactly same, okay, because if you look at this part of the Lagrangian, the upper part of the Lagrangian, sorry, Feynman diagram, this is exactly same in the both cases. The only difference that you see in this diagram is this part. Okay, only the leptons are different. We have different leptons in the final state. But if the interaction strength is same as we saw in standard model, then we expect them this branching ratios to be exactly same at the experiment. Okay, so this is a way to test it. So this is one way to test it. You can have other modes, for example, but this is a one of the way to test it. So similarly, in the there could be more new physics particles which could also mediate the same process. For example, you can have leptoquarks. These are the objects which couple to simultaneously couple to leptons and quarks. So for example, you can have this vortex B goes to L mediated by this heavy leptoquark, and this also give rise to B plus to K plus. But this new physics particles doesn't have to satisfy a priori lepton-flavour universality. Okay, so for example, they can couple, leptoquark can couple unequally to electrons and muons. So there is a possibility that you can break many ways this lepton-flavour universality feature of the standard model using different types of new physics. Further, this flavor changing, so as you see, this is a flavor changing neutral current, B plus to K plus. These are also interesting on their own rights because these transitions are very suppressed in standard model. And if you see any, so it's easy to see any presence of new physics in such decays. So these are sensitive to heavy particles, as I said in this demonstration. They can be sensitive to leptoquarks, for example. And the most important thing is that this kind of decays in which through this kind of decays you can probe the much higher energy scales.
I have a question. Was the branching ratio similar for both the diagrams, or was it just for the first one, or is it the same in leptoquark interaction as well?
Okay, so the first diagram, this diagram, is a standard model diagram.
Yes.
Okay, and this is an example of new physics diagram. Okay, in which is mediated by leptoquarks.
Yes.
So I explained in the previous slides that lepton-flavour universality is a feature of standard model.
Yes.
So that's why this only for this diagram, you expect the rate for B plus to K plus, mu plus mu minus, or B plus to K plus, E plus E minus to be equal, but not for the second diagram.
Okay.
Yes. Second diagram is a new physics diagram, and so this vertex, for example, if this vertex is different for B mu and BE. Okay, yes. So then this branching ratio will be different for E and mu.
Okay.
Yes. So this is a feature of only standard model. This is an accidental symmetry present in standard model only. Okay, in new physics it doesn't have to be present. So we want to see if it is we want to test the standard model using this kind of processes.
Okay, Jacky.
Yep.
So I think also for this one can also have this lepton-flavour violation, right? FFVs also. So
yes.
Expect that
so
to enhance, or there is some.
Okay. Yeah, this is also another interesting point. So if I go back to my interactions here, so you see that these interactions are diagonal in the flavor. Okay, so for this is always like a Z mu, E bar E, mu bar mu, or tau bar tau. Okay, so these are always diagonal in the flavors. That means in standard model, this lepton-flavour is conserved. There are no interactions like Z, E mu, or E tau. Okay, so these are basically, if you set neutrino masses to be 0, this kind of observables are identically 0 in the standard model. Okay, so these are, that means very, very suppressed modes in standard model. So this is another way to measure lepton. Yeah, so you can also measure this lepton-flavour number violation using similar decays. So in that case, you have to look at the experiment for, let's say, B plus to K plus E mu or E tau or mu tau. So these kind of things. So this is also but this is another feature of the standard model. But right today we want to focus on a particular feature of standard model, which is a lepton-flavour universality. Okay, but this is true. For example, this Leptoquark models, when you try to have a lepton-flavour universality violation using Leptoquark models, and usually they also introduce lepton-flavour violation. So this in fact puts a strong constraint on such models. For example, if you couple your Leptoquark to E and mu both, then lepton-flavour violation is automatically introduced in Leptoquark models. So this is a nice feature of Leptoquark models, due to which they are very constant. Okay, so we will move ahead. So I was saying that in addition to testing LFU, so in general, this kind of flavor violating modes, this can probe much higher scales as compared to LSC. So for example, you can have this modes mediated by some virtual particles which are very heavy, let's say 10 TeV, which you cannot produce directly at the Large Hadron Collider, but you can see their indirect signals using measuring these kind of processes. Okay, so now let us look at the what kind of observables we have. So as I said, we can look at B2S L plus L minus transitions. In particular, B plus to K plus, B plus mu minus, and B plus to K plus E plus E minus. So what you can do, you can construct a ratio of these two branching ratios. And this ratio, because E and mu behave identically in standard model, so the theoretical prediction for this ratio is 1 in standard model. And the theoretical error, as you can see, is very small. So what happens is that the errors in the numerator, so this decay is basically like this. So you have a mu plus mu mod in the numerator, and B2S E plus E in the denominator. So the penguin part, the upper part.
Jacky, hello.
Yes, sir.
Jacky, is any difference in these branching in these ratios due to phase space? I mean, that's very small.
Yes, exactly. So yes, so
quite a large difference.
Yes, so that phase space. So exactly, this is one of the way to break so this is one of the way to break this universality in standard model, but this is small. Okay, and this also depends on the momentum transfer. So we have a
so this B plus has a mass of about how much? 3 GeV?
Yes, like 4-5 GeV.
4-5 GeV. So this is about 2.2. 0.2 is fourth power or something. 0.2, but so I mean, how much you only expect to 0.01 kind of variation due to phase space?
Yeah, actually, this also depends on the momentum transfer. So we have a B going to K, and then there is a momentum transfer, okay, to the lepton sector. So depending on this Q score value, so this effect can vary.
So can you define it so that it doesn't care about the no? Anyway, so it's a small effect, you say.
Yeah, it goes something like this, I think. order ml square over mb square. So
And
that's
then-
why when they
So how much is that? ml square md square is about 0.2 whole squared. So it's about 1 by 20, 1 by 400. Okay, okay. So it's pretty small.
yeah
Okay, okay.
yes yeah it's visibly it's a very very small effect. Another way to break the similar thing is through Yukawas. So in standard model Yukawas as you know, Yukawa's interactions distinguish between E, mu, and tau, but that's again proportional to mass. So these two phenomena, so you can break these two ways, this lepton-flavour universality and standard model, but both are proportional to the lepton mass, and they are small effects. And as you can see, this from the prediction, this ratio is a theoretical prediction in standard model. This is one. This is one plus minus only 1% error. So this is in fact very very clean. These are very very clean tests of lepton-flavour universality. These ratios in particular. So you can also have similar ratios for B to K star, mu plus mu minus. This is a very similar mode, and here also the prediction for standard model is very very precise. So you can go on and construct more ratios, like you can have different channels. You can have BS0 in the initial state, and various type of hadrons like K plus, K0 in the final states. So all these ratios are very very clean tests of this feature of the standard model. And in fact, LSCB is the plan of LSCB is now, since they saw this deviation, now they are measuring more and more channels to test it independently. And the interesting thing is that coherently they see whatever they have measured till now, in all channels they see the discrepancy. So now let us look at the experimental status. So as I said, this all started with this RK measurement, which is B plus to K plus U plus mu minus divided by B plus to K plus E minus. Okay, so this is 1.1 also. So this is found to be 0.846 plus minus. So first error is statistical, and second error is a systematic error. So you see, systematic is quite under control. There's no much error. This all the uncertainty is only due to systematic error right now. So if you see this is about 3.61 sigma deviation with respect to standard model. So initially when it came in 2014 by same LSCB experiment, it was like 2.5. Then they have update in 2019. Then it stayed almost same 2.45. And then they had this update, I think, a few months ago. Now it has become 3.1 sigma. It has increased a bit. Similarly, they have measured B0 to K star 0, mu plus mu minus in this Q square, this bin 0.045 to 1.1 GeV square. And this is also found to be suppressed as compared to standard model. And this came in 2017. And after that, I think this is only, I think, most precise measurement of RK star. There are other measurements from Babar or Bell. I think they are not so precise, but this is about 2.2 to 2.4 sigma discrepancy. And similarly, they have also measured this same thing in other bins, and consistently they find discrepancy in all the bins. And very recently, LSCB has also measured B0 to KS, K short 0.
Jacky,
Yes.
these predictions you said were all, they should be 1, right?
Yeah, so these are
plus
experiments.
minus 0.01. So
Yes.
Here is 0.16, and theoretical error was only 0.01. So how do you roughly estimate the deviation? Because this deviation seems to be much larger, right? 0.85 and 1 is 0.15. that's almost a 15% deviation, whereas the theoretical error, these are the errors, so 0.04. I
Yeah.
see.
So for
it's about,
example, yeah.
Okay, you
Yeah.
do it in quadratures or something, then you get, okay. Okay,
Yeah,
thank
to
you.
get a rough estimate, you can do that, but LSCB can also, they can also do precise things, how to combine the errors.
Right.
But roughly this is 3.1 on the ballpark of 3.1.
Okay.
But the interesting thing is that you coherently see in all these ratios discrepancy. This is not only one channel, okay? You see coherently in multiple channels. So that's a interesting thing about it. So okay, so this is RKS, and they have also measured B plus to K star plus mu plus mu minus to E plus E minus, and so these last two decays came very recently, I think few weeks ago, and they show they are consistent with standard model at the level of 1.5 sigma. But as you see right now, they have much larger statistical errors. Theoretical error, systematic error is again under control, but they have, as compared to the other modes, they have much larger statistical error. That's why right now we cannot say much about it. So in future, I think they are going to, of course, improve it. So then when statistical error goes down, then we'll have better picture of these things. Also, we are expecting an update of RK star from LSB, I think in a year or so. Okay, so there are also, so this is what I showed only was from LSCB. There are other measurements from Bell, for example,
Jacky,
which are, yes.
Can you hear me? So I think maybe also about B5 prime and other variables also, right? There is also some discussion.
Yes, yeah, sure. So in addition to these ratios, there are also other observables. So basically what you can do, you can construct an okay, maybe I can write here. So you can construct, for example, B0 to K star 0, mu plus mu minus, and this decays to K pi. So we have 4 body final state, and you can construct angular distributions of these decays. And one of the observables in this angular distribution is known as P5 prime, which is also found to be discrepant. In fact, there are some branching ratios also which are found to be different from standard model. But in this talk, I mean, it's not so important to list all the anomalies, but we just want to see that how to interpret them, how to learn about lepton-flavour universality in general in the SMEFT. Okay, if this feature is found, but these modes also have the problem with the theoretical predictions, because the ratios in the ratios, if you see, yeah, in the ratios, these errors are theoretical errors, are hadronic uncertainties are mostly cancelled. That's why they are very clean. But for these pure modes like P2K plus mu minus, we have problem with this uncertainties. But interestingly, these some of these are also found to be different as compared to standard mode, and that's again only in the muon mode. Electron modes are found to be consistent, and that's why we see that there is something in the muon mode as compared to electron mode. So if you measure only the ratios, for example, if you found this ratio is suppressed, then either you can enhance your electron mode or suppressed muon mode. Okay, you will not know if you need any physics in electron or muon. You can have both. Okay, but since these branching ratios are also pure branching ratios are also found to be discrepant, so global fit prefers any physics in muon. So I will come to this in a moment when I come to the interpretations. Yeah, so now that we have seen that there seems to be some discrepancy with respect to standard model. So people have interpreted them, these discrepancies, in various models, the Leptoquarks, Z prime. These are the 2 prime candidates which can explain these anomalies. Also other particles like vector like leptons or quarks. But you can also do it in model independent fashion to see what kind of Loren structure you need to accommodate this data. So for that, first let us define most general Loren structures of effective operators. So you can write your effective Hamiltonian like this. These are O's are here higher dimension operators, and this is some normalization. You can choose any normalization, this doesn't matter. So this is chosen keeping in mind the structure of standard model, but you can have any normalization. So you can write your effective Hamiltonian Ci OI plus Ci prime and OI prime. So here primes are just chirality flipped operators. So if this operator O has a PL, so O prime has just PR, or if it has a PR, it has a PL. So we can have a structure, for example, this S bar sigma mu nu PRB and F mu nu. So these are known as the dipole operators, known by the name of O7 or O7 prime. If you replace this PL by PR, then you get O7 prime. But these are very, very severely constrained by B2S gamma. So there is no hope that this structure can give could help us to explain these anomalies, because these are already severely constrained by B2S gamma. Then you have O9. O9 is basically you have a left V minus A structure in the quark sector and a vector in the lepton sector. So L bar gamma mu L, and this operator in particular can contribute significantly to B2S L plus L modes. Similarly, we also have O10 in which gamma mu is replaced by gamma mu gamma 5. So we have a vector and axial vector operators. You can also write scalars S bar P R B L bar L, and again these are also very severely constrained by B sub S to mu plus mu 1s. So from these two operators, there is no hope. We cannot explain the anomalies using these two operators because these are very severely constrained. So we are left with O9 and O10, and in fact, we'll see that these if you allow a new physics in these operators, then you can accommodate the data very well. Okay, so this I wrote just a chirality flipped operators you can get by changing left right. So we have similarly here O7 prime, O9 prime, O10 prime, and OS prime. So only the blue ones are generated in the standard model. Okay, so other structures, OS scalars, or these are not generated in standard model, but in general they could be present. They could be present beyond the standard model. So so now these CIs are known as the Wilson coefficients. So these are basically coupling strength of these operators. So now let us look at what are the values of these C's in standard model. Okay, so in standard model you can calculate these C's perturbatively. So basically it goes through this box and penguin diagrams in standard model. So you can have a B going to S mediated by W and top. Here you can attach to, for the case of photon, you can attach to leptons. And similarly, you have this box diagram. So if you calculate them, so they will give rise to these dimension 6 effective operators, C9, C7, C9, and C10. And this has been calculated. And at the B mass scale, these are the standard model values. Of as you see, the C9 and C10 are quite big as compared to C7. Important feature that is you see here is that C9 here is almost equal to minus C10. So if I remind you, C9 was a vector. It was L bar gamma mu L for the leptons, and C10 was L bar gamma mu gamma 5L. So C9 equal to minus C10. That means we have almost V minus A structure in the standard model. So this is a nice feature. You see, okay, so standard model has a V minus A structure.
Hello.
Yes, yes.
So this V minus, due to this V minus is structure, in the last slide you have constructed some operators in last slide.
Yes.
Yes. So their dimension is
Mass dimension is a 6.
okay.
So fermions have a 3 by 2. So 3 by 2 times 4.
Okay. So this universality violation cannot happen at 5 dimension.
No, so the thing is that so yeah, so if you see this operator as per B F mu nu, this is formally dimension 5, right? So
Yes.
F mu nu is a field strength. So this is like goes a square, and this part is dimension 6. So this is dimension 5. Okay. Basically, this give rise to S to B B gamma. But gamma, as you know, is a universal. It couples to E, mu, and tau equally, and in standard model it's a universal. Okay, but it's possible that beyond standard model you can have a universality violation in this operator, because but these are, as I said, very severely constrained by bitwise gamma processes. So even if you allow new physics, and their values are very small, they are very tightly constrained.
So okay, right. So here this is kind of 4 lag interaction effective.
Yes, so our process at the quark level is B2S L plus L minus. So this is basically 4 fermions. Yes, you can think
So
of it as a,
for
yes.
yeah. So for this effective interaction, we have gamma 5 sigma mu like entities. So how can we interpret why these gamma 5 and sigma mu's are there? As you mentioned in last slide, B minus type structure. Uh,
Okay, so at this point, when I read O7, O9, O10, or OS, I'm trying to write a most general effective interactions. Okay, so you take S, B, or L, or photon. You take all the fields of your low energy theory and combine them in all possible ways, so that they satisfy Loren symmetry and
so
QCD.
there is some kind symmetry violation like when we in case of V minus structure we have 1 minus gamma 5 structure kind of
Yeah, so V minus A means basically vector minus axial vector. So if, so for example, here you have a PL, okay? PL is basically 1 minus gamma 5 by 2. So if you multiply by gamma mu, so this give rise to V minus A structure. So, but here in the lepton sector, the way we have defined them, we have defined O9 with only gamma 5 and O10 with gamma mu gamma 5. So in principle, if O9, the value coefficients of O9 and O10 are different, then it's not a V minus structure, V minus A structure, okay? But it turns out that in standard model, when you calculate the coefficients of these operators, they are found to be V minus A. But in general, when you add new physics, it doesn't have to be B minus A. It could be different. It could be linear combination of this.
okay, thanks.
Yeah. So basically, when you calculate these diagrams, you see you get these values. Okay, and from these values, you see they are almost and gamma mu and gamma mu gamma 5 operators are almost same. So okay, so people have so using this effective theory approach, people have performed global fits and found the allowed values of new physics Wilson coefficients, okay, which fit the data. So for example, if you fit C9 only, so you can fit with only RK star data, which are the ratios. And there are also other observables which like P5 prime or pure branching ratios. So we can divide data into 2 sets, like pure ratios and then other modes. And if you fit them, so you need this kind of values. You need a minus minus sign, and the value almost equal to 1. So you can have this discrepancy can be explained by C9, or also if you have C9 minus C10, which is a same structure as standard model. But you see this B2S mu plus mu minus data and RK star data, if you fit them separately, they are in slight tension with each other. So, okay, so you see the, if you fit to the global data, to the full data, then these are the values, desired values to fit the data. Here pool is defined to be chi-square standard model, so minus chi-square minimum after at the best fit point, and you see the pool is around 5.8 or 5.5. Different groups have got a little bit different pools. So what we learn that if we have a negative shift in C9 or C9 equal to minus C10 in the muon sector, okay, then you can explain the data. So that's our takeaway from this discussion. So it is, I mean, it is likely that new physics, there is a new physics in electron and muon mode both, okay. It doesn't have to be only in the muon mode. So one can try to fit electron and muon Wilson coefficient together and see if the fit improves, to see if you need new physics in electron as well. So in this fit, for example, you see you need a non-zero value of muon. Muon should be non-zero, but you can have a little bit preference of new physics in E as well. Okay, so these are various fits in different scenarios people have performed, and this particular fit is very interesting. So here, what people did, so they fit C9 equal to minus C10 muon versus C9 universal. So C9 universal means C9 mu is equal to C9 E. So in addition to this non-universal component, here you have C9 equal to minus C10 muon. They also allow a new physics in the universal C9 equal to minus C10. So as you can see, the fit prefers a non-zero value of C9 universal. So along with muons, there is a slight preference of new physics in C9, C9 universal basically. So now question is, you can ask question, what kind of new physics can offer C9? Well, we will discuss this when we go to our discussion of SMEFT in a moment. So till now I have summarized all the anomalies. So now we'll quickly go to the SMEFT part. Okay, so as you know, LSC is searching for, LSC is performing various kind of direct searches, looking for leptoquarks, Z primes, vector leptons, all sorts of particles, but it hasn't seen nothing right now. So this is a summary plot from CMS where you see the lower bounds on the masses of the particles. As you can see, currently this is around 10 TeV. So the masses, the lower bounds are pretty high. They are going pretty high. So if you compare it with respect to electroweak scale, so which is here around, which is around 100 GeV. So we see there might be this scale gap. LSC is indicating that there might be this scale gap between electroweak scale and the new physics scale. But I must tell you that this kind of this observation is a little bit, it depends on the assumptions, because when they interpret these bounds, they have some assumption on the couplings of these particles. So, but roughly this is a picture that bounds are getting higher and higher. So if we assume that for the moment that scale of new physics is much higher than electroweak scale, so then so we can imagine this kind of picture. So we have low energy scales like bottom mass and electroweak scale, and then some new physics scale which is unknown. So in this region, as you know, below the electroweak scale, SU3 color times U1 electromagnetic is unbroken. And in this region, the full gauge symmetry has to be unbroken. So if you integrate out if you have any particle that you introduced at this scale, z prime at scale lambda, then if you integrate out this particle, then what you generate are the effective operators which are invariant under this full gauge group. Okay, because at this scale, this full gauge symmetry has to be unbroken. So, for example, you will construct this kind of operators which are made up of the doublets. Unlike at the low energy where we have particles in the mass spaces. So for mu lambda, if lambda is really much larger than electroweak scale, as LS is indicating that, so we should really work with the gauge invariant effective operators at the new physics scale. So what Buchmuller and Euler in 1986, so they assumed that, let's say there's only field content of standard model, there is no new particle, new light particle. You have only like Q, L, ER, mu R, tau R, whatever fields we have in the standard model, keep on only these fields, and you respect the gauge symmetry and construct all possible operators, higher dimension operators up to dimension 6, and categorize them according to their dimension. So they listed all the dimension 6 operator in 1986, as you can see, but this was later corrected by Warsaw group. So now this is known by the name of Warsaw basis. So what you have is a standard model extended with the list of effective higher dimension operators. So this is effective field theory is known by the name of a standard model effective field theory, which has like 15 operators which are bosonic, and 19 which contains one single fermion, and there are lots of operators, 4 fermion operators, and this is without even flavor and color structure. If you put flavor and color structure, there are like 3000 operators. So let me just show you how the operator look like. So as you can see, you can have operators like this: Q bar Q, Q bar Q. You can construct with the leptons and quarks, L bar L, Q bar Q. So if you allow different Loren structures and up to dimension 6, so this is the list that you find. You can have more structures which are consist of Higgs fields or gauge fields. So these are basically 59 Loren structures that you can have. So this is a most general effective Lagrangian that you can write at scale lambda. So now, as you know, you have to renormalize your effective operators. So basically, when you calculate these one loop diagrams, so these diagrams will diverge, and then you have to renormalize it. Okay, and this causes the running of these operators. So basically, these C's are not constants; they depend on the renormalization scale, and this is governed by this normalization group running equation, which is basically a differential equation. So you solving them, you can find C as a function of mu. So this is basically a feature of renormalization that these Wilson coefficients run. And for SMEFT, this group, Jenkins, Alonso, and Monohor and Trott, they have computed full anomalous dimension matrix for the SMEFT, for the full basis of SMEFT. So any interactions that you introduce at the new physics scale, let's say you introduce 5 operators, C1, C2, C3, C5 at a new physics scale, then they will run. So, and they will mix with each other. So the picture at low energy can be totally different. So therefore, it is very important to include these RG running effects to correctly predict any features of new physics that you introduce at the high scale. So this is a general strategy that one follows in SMEFT. So we have a UV completion model, and assuming that all the particles are heavy, you can integrate them out and match your model to the SMEFT. So that will give you a standard model plus a series of higher dimension operators, which are invariant under the full standard model gauge group. Then you run them down using the anomalous dimension matrices. And at the electroweak scale, the electroweak symmetry is broken. And then below, we have a SU3 color times U1 electromagnetic as our symmetry. And you get a new effective theory which respects this symmetry instead of the full gauge symmetry. So here at this scale, you can match these two theories. So this is a very general strategy that one usually follows when you study any kind of decays. For example, low energy decays, delta F equal to 2 or 1 or 2 violation flavor violating decays, then you match your model to SMEFT, run them down to electroweak scale. At electroweak scale, you match it to another weak effective field theory and run them down to lower scales, and where you can predict the your observables. But in between, due to this running, many things can happen, as you will see. So what can we learn from SMEFT from LFU violation? So now we ask the question, if we use this most general theory framework, standard model effective field theory, and then in future, if this LFU violations are confirmed, so what we will learn from SMEFT? Because this is a model independent framework and most general framework, you can say, with some very reasonable assumptions which are supported by LSC. So what you will learn from LSC? So here I have 5 things which you will learn. First, due to SU2 invariance, you will see correlations with other observables. Okay, you can correlate these anomalies to other observables due to SU2 invariance, because your operators are SU2 invariance. Then due to SMEFT RG running at one loop level, you have even more correlations. So at one loop level, when you include RG effects, these decays can be correlated to even more observables. So then you will see that even how can you get this LFU universal contribution in C9? As I said in the when I explained the EFT interpretations, that fit data prefers currently, in addition to LFU violating component, you also need some universal component in C9. So you will see that in SMEFT through RG running, you can get this universal component. So now, and the fourth point, you will also see that you can generate flavor FCNCs using flavor conserving interactions. So at the high scale, you have flavor conserving interactions, you run them down, and due to running, you introduce flavor violation in SMEFT. And then finally, I will say that can bridge in low energy phenomenology and new physics models, okay, in a very model independent fashion. So to demonstrate all these points, we need just 2 operators. I showed you tons of operators, SMEFT operators, but let us work with only these 2 operators. Okay, these are semi-electronic operators, Q bar gamma mu Q, L bar gamma mu L. So this is SU2 singlet and this is triplet. Basically, this is only different that you have a tau I in addition to gamma mu here. So we will call them O1 and O3. So using these 2 players, we can explain all the features which I just mentioned. So say that you have our effective Lagrangian is like this, these 2 operators, which we call as O1 and O3, and they have coefficients C1 over lambda square. Here lambda is new physics scale. So since these are dimension 6 operators, so they have to suppressed by some scale. So they're suppressed by lambda square here, some general new physics scale. So now what you do, you expand these operators. Okay, so because these Q and L are here doublets, these are UL and DL, new and L. So these are doublets. When you expand them, so what you can, it is very easy to see if you put it here, and you will see that you can introduce B to S L plus L minus transition using these operators. But it is also very easy to see through this operator, because this has the Pauli matrices, and as you know, sigma tau 1 and tau 2 are off diagonal, so they are basically 0 1 1 0 0 minus iota 0 kind of structure. So you will also get interactions between up type up type and down type quarks. So this will also generate B2C. So just because of SU2 invariance, that means this two transitions B2S and B2C are correlated through this C3 Wilson coefficient. Okay, so due to this SU2 invariance, B2SLL and B2C, so this is charge neutral current mode and this is charge current mode. These are correlated through SU2 invariance. So one can show that using these two operators, one can explain both charge current and neutral current anomalies. This is well known. So now if you have, let's say, some model, U1 Leptoquark model, which generates this O1 and O2 operators at the high scale. So then you can correlate RD and B2K tau plus tau minus. So this is a charge current mode, as I said, RD, and this is a neutral current mode. So if I plot here the RD observable, which is basically B2 D star tau nu over B2 D star L nu ratio. So if you plot this as compared with the B2K tau plus tau minus, so you see if you demand any deviation from standard model, because standard model value is almost 1. So if you demand, for example, 20% deviation in RD star, so you predict about 250 times enhancement in B2K tau tau mode. So this is just because of SU2 invariance. So these are interesting correlations. So for example, if these anomalies are confirmed RD star, you must also see a huge enhancement in B2K tau plus tau modes. Okay, so that was only tree level. Now at one loop level. Okay, so consider again the same two operators, O1 and O3, and now you normalize them. Normalize them means you compute the diagrams like this, and you will see that at one loop level, if you insert this operator here, so basically you have LL here and close the quark loop and attach a B or a W gas boson. Then you generate basically 4 Fermi operators. Here, if you couple it to L plus L minus, you generate 4 Fermi operators. That means if you calculate this diagram, as you know, this diagram will diverge. Okay, you will need that's why you will need a counter term. So you will need to renormalize this semi-leptonic operator, you need a counter term for the purely leptonic operator. So in technical language, we say that these operators, this O3 has mixed with this purely leptonic operators. So at one loop, the two things happen. One, you have a corrections to the Z boson vertex. So here, as you can see, we have a correction to the Z boson vertex at one loop level. And also this O1 and O3 mixed with purely leptonic operators. So now that means if you have semi-leptonic decays like B2SLL or B2C tau nu, at one loop level, these are correlated to purely leptonic modes, because at one loop level, this leptonic operator is generated. So this gives rise to lepton-flavour violating decays at one loop level. So in fact, people have found that there are these models, Leptoquark models, if they couple only to third generation, and if you take into account these RG running effects, then this basically excludes this model. So here, for example, in this plot, you can see RD observable versus RK observable. And here at this point, this is the experimental point. You need like 25% enhancement in the RD observables and like 20% suppression in the RK observables. And these are these points referred to the U1 Leptoquark model. As you can see, this is very, very severely constrained by this tau2 E nu bar and tau2 3 mu. Basically, it's excluded. This green region is much away from by many sigmas from the experimental point. So this model, when it came, the third generation, it made a big splash that it's a nice model. when new physics couple only to third generation, you can explain the anomalies. But then people, some Italian group, they found that if you include RG running effects, then it's basically excluded. Okay, so now let us come to the third feature. I think we are running a little bit late. I started, I think, 2-3 minutes late, so we can. I will finish soon. So, yeah. So, as I said in the beginning, that from low energy fields, we need some kind of lepton-flavour universal contribution to C9. So now in SMEFT, you will see that you can get this universal contribution at one loop level. So basically, what you have to do is start with this operator, dimension sequence operator, and again renormalize it. Okay, which you have to do anyway. So you insert it here. Here box represents this 4 Fermi attraction, and you close the loop and attach to leptons. So if you start with, let's say, 2-3 means 2-3 means S bar B and tau 3-3. So and close the loop. But here B and W couple to all leptons, okay, universally. This is just a feature of standard model because this is a standard model vortex. So this coupled to equally to E and mu. So in this way, from this operator, you can, from 2-3 operator, you can generate a universal contribution to, if you calculate this diagram, you get a universal contribution to this and these two operators. So at one loop level, this is a way to get this contribution. Yeah, this is just a fit. If you perform a fit in the plane of these two observables. So these are the, on the y-axis, these are two direct contributions. This is 2-2-2-3. That means mu SB. So these are the direct contribution to B2SLL. And this is 3-3-BS. So at one loop level, as I explained, you can get 2-2-SP here also. So this is a way to get the universal contribution that we saw in the beginning, that we need some kind of universal contribution. Okay, so now you can also introduce FCNCs due to by just flavor conserving interactions. So as you know, the gauge sector of standard model respects U35 flavor symmetry, which is broken by Yukawas. So if you look at this gauge sector, this each of the field you can transform by a unity transformation. Let's say U1, U2, U3, U4, and Lagrangian remains invariant. So we say that it has a U35 flavor symmetry. So to define your operator at the high scale, you need to choose some basis for these quarks, right? You have to choose some basis at the high scale. And since we are interested in down sector, so we can choose a basis in which down quarks are in flavor in the mass eigenstates and up quarks are not. So at the high scale, the structure of our Yukawas will look something like this. Okay, so we have YD is diagonal and YU is CKM dagger times the diagonal part. But the point is that even if you start with this diagonals, this particular basis at the high scale, and you run them down, just the Yukawas, okay, standard model Yukawas, you run them down, they become non-diagonal at the electroweak scale. So this is a value of Yukawas at electroweak scale as a function of Yukawas at the Nifi's scale. And this is a one loop part which you introduced to running. So you see that your Yukawas are under RGs, they become non-diagonal. They introduce, you get some non-diagonal component due to RG running. That means what basis you chose at the high scale, you have to rediagonalize the Yukawas at the electroweak scale, which is equivalent to defining your fields once again in the electroweak scale. And that's why you have to redefine your operators. And this thing introduces flavor violation, additional source of flavor violation in the SMEFT. So for example, here you can see, so if I start with a totally flavor conserving operator, okay, 2-2-2-2, and this also contributes to B2SLL decays at the low energy. Just this is just due to RG running. this operator 2, 2, 2, 3, it violates flavor, but this one doesn't violate the flavor. So this is obviously this contributes, but this this gives to contribution due to only due to RG running. Okay, so my final point is that since we are running out of time, so SMEFT can also act as a bridge, a sort of bridge between the new physics and the low energy phenomenology. So you introduce any kind of new physics at the high scale like Leptoquarks, Z primes, and match it to SMEFT, and then run them down. Here you see WZ resonances. So this acts as a bridge between new physics and the low energy phenomenology. Like the Fermi theory. Fermi theory was when standard model was not known, then you could study these B-decays using Fermi theory. So at that point, Fermi theory was very useful to test the standard model. So in similar fashion, now SMEFT can play a similar role to test the new physics or to know the structure of new physics. Okay, so that's all. Thanks for your attention. If you have any more questions.
Thank you, Dr. Jacky, for such a wonderful talk. So any questions or comments, please go ahead.
I wonder, is anybody making a comment?
Yes, please go ahead.
Okay, excellent talk. I must say, I was very also impressed by your last transparencies, which I borrow from you, referring properly to you, of course, of these mountains. No, I think it's, you know, this is, I wanted only to make two comments that the situation is very interesting now with these anomalies, but probably will be even more interesting in a few years where we will get, first of all, the results on B physics from Bell 2, which I hope will not exclude everything that LHC found. And so, what is also important from K physics. I think this is K pi neutrino antineutrino and K long. This will probably take pi 0 neutrino antineutrino. This will take longer time. I mean, the branching ratio is smaller. And I believe what Jacky already said, but in addition, these correlations, not only because of SU2 left symmetry, but also of some flavor symmetries. And this will maybe, you know, if we have more data, we can maybe exclude certain scenarios which people suggested for anomalies. I just want to make one comment, although this is controversial and I'm biased on that. And there is this CP violating ratio epsilon prime over epsilon, where I claim there is anomalies. Some other people claim there is no. But this is very difficult because these are non-leptonic decays, so this non-perturbative QCD. But the thing is, what I found with one of my PhD students, he's now 45, so Christoph Bobet, was that if you want to explain epsilon prime over epsilon, the anomaly which I claim, with the help of Leptoquark models, which are maybe favorite for these anomalies in B physics.
Yeah, this U1 is favored, yes.
Yes. Yes, then the thing is the following. Most of the models cannot explain epsilon prime over epsilon because it would violate already existing bounds on rare kaon decays. If you want to do, and maybe what Jacky was praising, this U1 model, this is maybe the model which maybe has a chance because it's not yet ruled out through epsilon prime over epsilon, okay, assuming that there is this anomaly, because at 3 level it doesn't couple to neutrinos, and this is maybe a chance, but one has to do still some maybe better analysis of this. Okay, so this is what I wanted to say.
Okay. Yeah, this is there's one related comment. So this U1 model at tree level, for example, it doesn't give rise to B2K unibar. If you see in my screen,
Exactly. So this is
so
one.
this is zero at the
Yes, yes.
yeah. But at one loop level, you get, and this is also a way to test it. So this
No, no,
predicts.
but I agree. But the thing what we found, I mean, this was really the problem with this factor U1, unless you have some UV completions, there is a problem of renormalizability. And so you really have some UV completion to do it, and people are playing with that. But we checked a bit at one loop level, and still at one loop level, there is no problem with this model, even if it would explain these anomalies. There is some correction, as Jacky said, we will test it, but maybe one should do better analysis of this U1 anyway. But I think just, I'm an old guy. I worked for 40 years on flavor physics. But I believe the next years, at least this decade, will be very exciting, because not only Belgium 2, but G-2 and everything. I think this will be a fantastic decade. So if there are some young people in the audience, work on flavor physics. This is the future.
Some of them are already working, I think.
I know. I cannot see them. This is the problem of all these meetings. You can travel to India in 1 second or 2 seconds, but you cannot see each other. And even, let me tell you the following: I don't like talks like this very much, because if I give the talk, listen, it's no problem. But the problem is, even if you give it in person, which I did recently, and if you tell jokes, you cannot see whether people are laughing, because they all have masks. So you don't even, if the joke is very good, you hear it. But if they're smiling, you cannot see it.
Yeah, here you don't see no reaction. Yes.
Yeah, that is true. Yeah.
Okay, thanks a lot.
Thanks for coming.
Yeah. Okay. So any more comments or questions? So, okay, if not, so thanks again, Dr. Jacky, for such a wonderful talk. And thank you, Professor Andres, for joining us and for the comments. Okay, then maybe you can stop this.